Hello and welcome to the Sleepy Journal, your quiet corner of the cosmos, where science whispers and wonder tucks you in. I'm so glad you're here. Whether you're winding down after a long day or drifting gently into dreams. Tonight, we're going to float through something very close, very familiar, yet endlessly fascinating. But first, a gentle question, our little bedtime ritual. Where in the world are you listening from, and what time is it right now? Let me know in the comments below. And if you enjoy tonight's voyage, consider giving this video a gentle like and perhaps subscribing to the channel. It helps more sleepy minds find their way here. Now then, let's begin. Have you ever watched clouds gather like slow thoughts across the sky, or felt thunder hum beneath your bones, like the earth clearing its throat? Weather is more than just what happens outside. It's the breath of our planet, the shifting moods of the sky, the swirling poetry of temperature, pressure, and time. And I do hope this isn't so interesting that it keeps you awake. But if it does, at least you'll learn something beautiful. So settle in, breathe slowly, close your eyes if you'd like. Let's drift into the science of storms, sunlight, and sky whispers. Let's begin. Chapter 1. What is weather? A human story of sky and skin. Imagine a child standing at the edge of a porch, their bare feet on cool concrete, looking out as rain begins to fall. The sky has darkened, birds have quieted, and the first droplets tap gently on the roof, like fingers testing the rhythm of the world. That child doesn't need a meteorology degree to feel something important is happening. Weather speaks to us before we understand it, in goosebumps and sunburns, in windblown hair, and the sudden hush before a storm. So, what exactly is weather? At its simplest, weather is the condition of Earth's atmosphere at any given moment in a specific place. It's the sum of temperature, humidity, precipitation, wind, visibility, pressure, and cloudiness, all dancing together in a symphony that changes by the hour. While climate is the pattern over decades, weather is the mood of the day. But that's just the definition. The deeper truth is that weather is experience. It's not a distant force we merely observe. It's something we live inside of. We feel it on our skin. We plan our lives around it. We write poems and songs about it. It shapes how we dress, how we move, and even how we feel inside. A gray, rainy morning can wrap us in quiet introspection. A golden spring breeze can unfurl the tight buds of our thoughts. Weather colors the canvas of our lives, moment to moment. And yet, beneath its soft touch and sudden moods lies a delicate choreography of physics, heat, and invisible air currents. Weather begins with sunlight. That great burning star, 93 million miles away, shines down unevenly on our spinning Earth. Some places receive more sunlight than others, equators more than poles, valleys more than mountains, oceans differently than land. This uneven heating is the root of it all. When one patch of air warms up, it becomes lighter and rises. Cooler air rushes in to take its place. This simple act, warm air rising and cool air sinking, sets the atmosphere in motion. It's the first breath of what we'll come to call wind. Add moisture from oceans and lakes, and you've invited clouds to the dance. Our planet's rotation adds a twist to this movement, literally. The Coriolis effect, caused by Earth spinning beneath the moving air, curves wind patterns into great swirling systems. It's why hurricanes spin in elegant spirals, and why trade winds flow with such stubborn direction. From there, weather unfolds as a kind of atmospheric storytelling. Temperature influencing humidity, pressure guiding wind, moisture becoming rain or snow depending on altitude and season. Thunderstorms, blizzards, heat waves, and gentle spring showers are just different expressions of these elements combining in endlessly varied ways. But for all its complexity, we often meet weather in the simplest of ways. A mother warns her child not to forget an umbrella. A farmer glances at the sky, scanning for signs of coming rain. Two strangers might talk about nothing else. Can you believe this heat? And feel suddenly connected. In fact, talking about weather may be the most universal conversation on Earth. It's neutral ground, shared reality, a way of saying, I'm here with you. I feel what you feel. And weather has shaped more than just our chats. It's shaped civilizations. Entire crops depend on timely rains. Ancient migrations followed winds and seasonal patterns. Battles were won or lost based on fog or frost. Even myths were born from weather. Gods of thunder, storms as omens, rainbows as divine promises. In every culture, weather has had a place at the spiritual table. It's no wonder. It's powerful, unpredictable, and beautifully beyond our control. It humbles us. In the modern world, weather feels more like a forecast than a force. We carry it in our pockets, apps telling us when it might drizzle or shine. Satellites peer down with tireless eyes, and supercomputers predict the winds before they rise. But even now, with all our tools and models, weather retains a sliver of mystery. A sudden shift in wind, a rogue cloud, a storm that forms faster than we can measure. There's something poetic about that. In a world of schedules and precision, weather reminds us that nature still has its moods, still surprises, still speaks in whispers and roars. And so we find ourselves here, curious minds lying back beneath a wide sky, wondering not just what weather is, but how it works. How can something invisible shape so much? How can a gust of wind come from thousands of miles away? What makes a cloud form, or a thunderstorm awaken? Those answers live in layers, of science, of air, of time. So let's dive deeper. We've felt the weather on our skin. In the next chapter, we'll climb higher, to the early thinkers who first dared to ask what made the heavens move, and how humanity's understanding of the atmosphere grew from myth to measurement. But before we ascend into history, take a breath. Let the room you're in feel like the eye of the storm, calm, centered, steady. The clouds outside may be shifting, but in here, we float gently onward. Chapter 2. A History of Sky Watchers, from Omens to Observations. Long before satellites orbited the Earth, long before radar pulsed through clouds, humanity had only one tool for understanding the weather: the naked eye. Imagine, if you will, a shepherd thousands of years ago, standing beneath a vast and endless sky. There are no forecasts, no instruments, just instinct and attention. The shift in wind, the scent of approaching rain, the color of clouds near dusk, all were read like ancient scripts across the sky. To survive, to plant, to fish, to travel, people had to become poets of the atmosphere. Weather was not just nature, it was divine. Storms were anger, droughts were punishment, and rainbows were promises. For early civilizations, weather was deeply spiritual, a language spoken by gods. The Sumerians, who flourished in Mesopotamia around 4000 BCE, worshipped Enlil, the god of wind and air. The ancient Greeks feared and revered Zeus, master of thunder and lightning. In Norse mythology, Thor's hammer sent storms crashing down from the heavens. And the Mayans carefully tracked the cycles of rain, knowing that timely storms meant bountiful harvests, and that the gods must be pleased. For these early skywatchers, weather wasn't just background noise, it was fate itself. And yet, alongside myth and ritual, curiosity stirred. As civilizations grew, so too did their hunger to understand the heavens not just through stories, but through patterns. The Babylonians, around 650 BCE, began keeping some of the earliest known weather records. They noted cloud shapes and storm frequencies, hoping to find order in the chaos. Some of their observations were surprisingly accurate. They linked red skies with incoming storms and halos around the moon with rain. It wasn't scientific yet, not in the modern sense, but it was a first attempt at forecasting. In ancient China, weather played a crucial role in governance and the cosmic order. The mandate of heaven, a divine right to rule, was believed to be reflected in natural harmony. Floods, droughts, and eclipses were signs that a ruler had lost the favor of the heavens. As early as 300 BCE, Chinese scholars used primitive rain gauges and wind vanes. The philosopher Wang Chong, in the 1st century CE, even questioned superstitions around thunder, proposing that it was a natural, not supernatural phenomenon. A bold idea for its time. Then came Aristotle. In 340 BCE, the Greek philosopher compiled centuries of observations and speculation into a treatise called Meteorologica. The name lives on in the word meteorology. In this early weather book, Aristotle pondered everything from rainbows and due to earthquakes and comets. He believed that all weather phenomena came from interactions between the 4 classical elements: earth, water, air, and fire. While many of his explanations would later be proven incorrect, his attempt to categorize and explain the atmosphere was revolutionary. Meteorologica remained the authority on weather for nearly 2,000 years. But Aristotle's influence didn't mean people stopped looking up and wondering. During the Islamic Golden Age, roughly 8th to 14th centuries, scholars preserved and expanded upon Greek texts. Persian polymath al-Biruni described atmospheric pressure and hypothesized about how altitudes affected the boiling point of water. ideas that wouldn't be proven until centuries later. Meanwhile, in Europe, the Renaissance sparked a rebirth of observational science. In 1607, Galileo Galilei, the same man who turned his telescope to the stars, also invented one of the first thermometers. It used air expansion to measure changes in temperature. It was simple, but it marked the beginning of instrumental weather science. In 1643, Evangelista Torricelli, a student of Galileo, created the barometer, a device to measure air pressure. "We live submerged at the bottom of an ocean of air," he wrote. "And that ocean, we would come to learn, ebbs and flows just like the sea, creating the very storms and breezes we feel on our skin." By the 17th century, instruments were whispering secrets of the sky. The thermometer and barometer were joined by the hygrometer to measure humidity and anemometer to measure wind speed. For the first time, weather could be measured, not just witnessed. Still, forecasting remained elusive. Even into the 18th and 19th centuries, predictions were based more on patterns and proverbs than data. Sayings like "red sky at night, sailor's delight," or "when the wind is in the east, 'tis neither good for man nor beast," held some truth, passed down through generations of observation. Farmers, sailors, and travelers lived close to the sky. They learned its moods the way one learns a partner's silence or sighs. Then, in the 1800s, something changed. A new technology emerged that would shrink time and space: the telegraph. With the telegraph, weather observations from distant cities could be shared in near real time. Suddenly, it was possible to track a storm as it moved across the country. In 1854, British Vice Admiral Robert Fitzroy, also known for captaining Darwin's voyage aboard the HMS Beagle, founded the first National Weather Service in England. He issued the world's first daily weather forecasts in the Times newspaper, based on real-time observations collected via telegraph. Some laughed at him. "Weather can't be predicted," they said. But Fitzroy persisted. He believed that science could save lives, especially those of fishermen and sailors who too often died in surprise storms. His storm warning systems and barometric forecasting marked the dawn of modern meteorology. Sadly, Fitzroy's work was not always appreciated in his lifetime. Ridiculed by the press and struggling with mental health, he died by suicide in 1865. But today, he is remembered as one of the founding fathers of weather science. His legacy lives on in every forecast that warns of a storm before it strikes. By the 20th century, weather balloons were reaching the upper atmosphere, carrying instruments to measure temperature, pressure, and wind at altitude. The invention of radar during World War II allowed scientists to peer into storms, seeing rainfall and wind like never before. And in 1960, the first weather satellite, TIROS-1, was launched into orbit, offering a god's-eye view of the Earth's ever-changing skies. From cave paintings to computer models, the story of weather science is the story of human curiosity. Each new invention, each new question, brought us closer to understanding the moods of the air above us. But we've only just begun. In the chapters to come, we'll follow the life cycle of weather systems, from the heat of the sun to the swirl of hurricanes. We'll float with clouds, dive into jet streams, and watch lightning thread across the sky like nature's own handwriting. But for now, breathe in. Imagine all those ancient skywatchers standing quietly beneath their skies. In some small way, we're still standing beside them, heads tilted back, eyes soft with wonder, asking the same timeless question. What's happening up there? Chapter 3. The Sun's Secret Role in Weather, the Star That Stirs the Sky. Far above the clouds, beyond the grasp of weather itself, burns a quiet constant, the sun. To our sleepy eyes, it may seem like just another part of the morning routine, rising, setting, rising again. But in truth, this star is the hidden hand behind every breeze, every thunderstorm, every snowflake drifting through the hush of winter. Weather, at its heart, is the story of energy moving through the atmosphere. And the sun is where that story begins. Let's start at the very beginning, at the surface of the sun, where temperatures soar to around 10,000 degrees Fahrenheit, and deeper still, where nuclear fusion churns endlessly in its core. Every second, the sun fuses about 600 million tons of hydrogen into helium, releasing unimaginable amounts of energy in the form of heat and light. That light travels 93 million miles to reach Earth, a journey of about 8 minutes and 20 seconds. But once it arrives, it doesn't fall evenly across the planet. And this simple unevenness is where weather is born. Picture the Earth as a softly spinning sphere. Its tilt, about 23.5 degrees. Means some places are bathed in direct sunlight while others receive only a slanting glance. Equatorial regions soak in heat year-round, while the poles linger in long shadows. Oceans absorb warmth differently than forests, deserts differently than cities. Mountains cast cooling breezes. Valleys trap warmth like a sleeping body under a thick quilt. This unequal heating creates pressure differences. Some parts of the atmosphere warm and rise, while others cool and sink. These rising and falling pockets of air set the atmosphere in motion, like bubbles rising in a pot just before it boils. Warm air, being lighter, rises from the heated surface. As it lifts, it expands and cools. Meanwhile, cooler, denser air rushes in to fill the space left behind. This cycle creates convection currents, endless loops of rising and sinking air, that drive everything from gentle sea breezes to towering cumulonimbus clouds. And the sun doesn't stop there. It also fuels the great global conveyor belts of wind. Around the equator, where sunlight is most intense, warm air rises in a belt called the Intertropical Convergence Zone, or ITCZ. This rising air causes thunderstorms and frequent rains, explaining why tropical regions are lush and verdant. As this air rises, it moves poleward, cools, and sinks around 30 degrees north and south of the equator, forming what we call the Hadley cells. These cells, in turn, drive the trade winds that carried ancient sailors across oceans and still guide tropical storms today. Higher up, at mid-latitudes, the Ferrel cells churn, and beyond them, near the poles, the polar cells spin. These vast, invisible loops are Earth's attempt to balance the books, to move excess heat from the equator toward the poles and cooler air in the opposite direction. All of it powered by the sun. But there's more to the story. The sun doesn't just heat the air, it stirs the oceans too. Oceans cover over 70% of Earth's surface, and they act as massive heat reservoirs. Sunlight penetrates the upper layers of water, warming them. Warm water evaporates more easily, releasing water vapor into the air. This vapor is the raw material of clouds, fog, dew, and rain. Where the ocean is especially warm, like the tropical Pacific, vast systems like El Niño are born. El Niño, and its cool counterpart La Nina, are global weather influencers, altering rainfall patterns, hurricane paths, and even seasonal temperatures on distant continents. These ocean-atmosphere interactions are delicate and complex, but they all begin with sunlight warming water and water answering with clouds and wind. Have you ever stepped outside on a summer afternoon and felt the heat press into your skin? That's infrared radiation, part of the sun's spectrum, warming your body just as it warms the earth. That heat is absorbed by the ground, then re-radiated back into the atmosphere, often as long-wave infrared energy. This re-radiated energy interacts with greenhouse gases like carbon dioxide, water vapor, and methane, trapping heat and gently warming the planet. This process is natural, necessary, and ancient. Without it, Earth's average temperature would be a frigid 0 degrees Fahrenheit, far too cold for the life we know. But today, as we add more greenhouse gases through industry and deforestation, we're tipping the balance. The sun hasn't changed, but the way Earth holds its warmth has. This imbalance is at the heart of our current climate crisis, but we'll visit that more deeply in a later chapter. For now, let's return to something quieter. Imagine a sunrise. As the sun lifts over the horizon, light begins to warm the land, slowly at first. The air nearest the ground stirs, heated from below. Tiny thermals, columns of warm air, begin to rise. Birds ride them like invisible elevators. As the day unfolds, these thermals grow stronger, setting clouds in motion and awakening breezes. All of it from the morning light. On larger scales, this same process creates monsoons. In places like India and Southeast Asia, the seasonal cycle of solar heating leads to dramatic shifts in wind and rain. During summer, land heats more quickly than the ocean. Warm air over land rises, drawing in moist air from the sea. This moist air climbs, cools, and unleashes torrential rains that nourish crops and shape cultures. Then in winter, the process reverses, and dry winds sweep outward, all orchestrated by the slow, steady drumbeat of solar rhythm. Even the gentle sea breeze at the beach is a sunlit ballet. As land heats faster than water, air over land rises and pulls in cooler ocean air to take its place. By evening, the process can flip, as land cools quickly and water retains its warmth. The breeze shifts and night settles in. Isn't it beautiful to think that the sun, from nearly 93 million miles away, can create a sigh of wind at your cheek? Even storms, those fierce moments of atmospheric drama, owe their power to the sun. Thunderstorms form when warm, moist air rises rapidly. The more heat, the more lift. As that air ascends, it cools, condenses, and releases latent heat, adding fuel to the fire. With enough instability, towering cumulonimbus clouds explode skyward. Lightning crackles, thunder rolls, and rain falls in sheets. Yet at the heart of it all is warmth rising, sunlight remembered. The sun doesn't create weather directly. It doesn't send rain or carve wind by hand. But it sets the energy in motion. It lays the tracks and gives the train its first push. In that sense, the sun is less a painter and more a composer, writing the score, setting the tempo, letting the atmosphere play its own instruments across oceans and plains. And so, next time you squint at the morning sky or feel the first warmth on your face, remember, you're standing in the presence of the great conductor of Earth's atmosphere. Every weather event, from the quietest dew to the loudest thunderclap, echoes with the sun's subtle rhythm. Now, with the sun as our guide, we're ready to descend a little into the air itself, into clouds, into pressure, into the very breath of weather. Chapter 4. Clouds, Currents, and the Breath of the Sky. Look up on a lazy afternoon and you'll see them, clouds, drifting like thoughts across the blue expanse. Some are soft and cotton-like, others stretch like silk ribbons, and still others tower like castles of vapor. They seem so light, so peaceful. And yet, within their shapes lies the key to understanding the breath and pulse of our atmosphere. To understand clouds, we must first understand the air itself, the invisible ocean in which we live. Air is made mostly of nitrogen and oxygen, with a sprinkling of argon, carbon dioxide, and water vapor. Though it feels light and ethereal, it has weight. That weight, pressing down on us from all sides, is atmospheric pressure. At sea level, the air above us weighs roughly 14.7 pounds per square inch. That's like carrying a bowling ball on every square inch of your skin, though we don't feel it because that pressure is perfectly balanced inside and out. But change that pressure, even slightly, and the weather shifts. High pressure acts like a blanket, pressing down on the atmosphere. It stifles cloud formation and usually brings fair weather. Low pressure, on the other hand, lifts the blanket, allowing air to rise, expand, and cool, making it easier for clouds and precipitation to form. So what causes those changes in pressure? The answer circles back to the sun. When sunlight heats the earth unevenly, it creates warm and cool patches of air. Warm air rises, reducing pressure near the surface, while cool air sinks, increasing it. These pressure differences set the atmosphere into motion, creating wind. Think of wind as the sky breathing. It flows from areas of high pressure to low pressure, trying to smooth the imbalance. The greater the difference, the faster the wind. Sometimes it whispers. Sometimes it roars. And when wind carries warm, moist air upward, something magical happens. As air rises, it moves into regions of lower pressure. It expands, and as it expands, it cools. Cool air can't hold as much moisture as warm air, so the water vapor begins to condense, first into tiny droplets, then into visible cloud structures. Each cloud droplet is born around a tiny particle, a speck of dust, salt, or even pollen. These are called cloud condensation nuclei. Without them, the water vapor might remain invisible, suspended in the air. But with these tiny seeds, clouds can bloom. Clouds come in many forms, and each one tells a story. Cirrus clouds, high and wispy, form where the air is cold and dry. They're often the first sign of an approaching system, whispering change on the horizon. Cumulus clouds, those fluffy cotton balls, are the ones children draw and daydreamers follow. They're born from warm rising air and often mark fair weather, unless they grow too tall. Stratus clouds stretch in low, gray blankets, turning the sky into a soft monochrome. They're often the authors of drizzles and gentle rains. Cumulonimbus clouds, however, are the giants. They rise like mountains into the sky, sometimes reaching over 60,000 feet. Inside them, updrafts, downdrafts, ice crystals, lightning. They are the cradles of thunderstorms. Clouds aren't just decoration. They're the architecture of the atmosphere, shaped by air pressure, wind currents, temperature, and terrain. They regulate Earth's energy balance, reflect sunlight, trap warmth, and carry moisture across continents. Imagine a cloud forming over the ocean. Warm air, moist from the sea, rises and cools. A cloud takes shape and is carried by trade winds inland. It grows, stretches, and finally, somewhere over a forest or a mountain range, it releases its moisture as rain. That water nourishes the soil, feeds the rivers, and eventually returns to the ocean to begin again. This cycle, the water cycle, is one of the most elegant and vital systems on Earth. It begins with evaporation, driven by solar heat. Water turns to vapor, rises, condenses into clouds, and falls again as precipitation. Some of it soaks into the ground, replenishing aquifers. Some flows into streams and rivers, and some evaporates once more. A never-ending circulation, quietly sustained by the breath of the sky. And that breath is not uniform. Around the globe, large-scale wind patterns create ribbons of air that shape the flow of weather systems. One of the most important of these is the jet stream. Jet streams are narrow bands of fast-moving air found high in the atmosphere, typically between 30,000 and 40,000 feet. They form at the boundaries of major air masses, like the cold polar air and warmer mid-latitude air. Fueled by temperature contrasts and Earth's rotation, these streams can reach speeds of over 200 miles per hour. They meander like rivers in the sky, steering storms, influencing airline routes, and even affecting temperature patterns far below. When the jet stream dips, it can pull Arctic air deep into lower latitudes. When it stalls, it can trap heat or moisture in place, causing prolonged droughts or floods. The jet stream is, in a way, the sky's conductor, directing the movement of air masses, shaping the rhythm of the weather. And yet, even small things affect this great breathing system. Mountains can redirect wind, causing air to rise and cool, creating clouds and rain on one side and dry, warm conditions on the other. Cities, with their concrete and steel, can form urban heat islands, altering local airflow and even changing when and where rain falls. Trees, lakes, valleys, and coastlines all leave fingerprints on the wind. Weather is not just global, it is intensely local. A gust of wind you feel on your cheek may have come from miles away, or it may have just slipped around the corner of your home, born from the warmth of a sunlit wall. So much of this system remains invisible. We can't see air pressure. We don't notice the weight of the atmosphere. We don't see moisture until it gathers in clouds. And yet, it's all around us, moving, whispering, shaping the world in soft, unseen ways. That's the beauty of atmospheric science. It teaches us to look again at the familiar, to listen to the invisible, to understand that even the quietest gust of wind carries stories from faraway seas. So next time you gaze up at a cloud, whether it's a wisp or a thunderhead, remember what you're really seeing: water, sunlight, motion, and breath. The whisper of oceans, the warmth of land, the slow heartbeat of the sky. Now, having floated among clouds and currents, let's step closer to one of weather's great marvels, the gathering of storms. What makes the sky suddenly darken? What awakens the thunder and lightning? What turns calm into chaos? Chapter 5, Storms and Thunder, When the Sky Speaks in Fire. There comes a moment, quiet at first, when the sky darkens like a mood shifting. The wind grows still. Birds vanish. Leaves flip to show their pale undersides. And then far off, a deep, slow rumble, like the earth itself is clearing its throat. A storm is coming. Storms are not just weather. They are performances. Tension, rise, climax, release. And behind their spectacle lies a choreography of air, water, and energy, precise, powerful, and profoundly poetic. Let's begin with the birth of a thunderstorm. All it takes is 3 simple ingredients: moisture, rising air, and instability. First, moisture. This usually comes from large bodies of water, oceans, lakes, or even wet land. Sunlight heats the surface, causing water to evaporate. That vapor rises, carrying hidden heat, the so-called latent heat, with it. Second, rising air. Often, this is provided by daytime heating. As the sun warms the ground, the air above it also warms and becomes lighter, rising like a balloon. Sometimes it's helped by a cold front, an advancing mass of cool air that forces warm air upward like a ramp lifting a car. Third, instability. This means the atmosphere is ready to support vertical motion. In an unstable environment, once air starts rising, it keeps rising, accelerating as it goes, like a spark catching dry wood. As moist, warm air climbs higher and higher into the sky, it cools. The water vapor condenses into clouds, releasing its stored heat. This heat, in turn, warms the surrounding air, making it rise even faster. It's a chain reaction, an upward cascade. From a distance, you might see a flat-bottomed cumulus cloud suddenly grow skyward, puffing and stretching until it becomes a towering cumulus congestus. If the conditions are just right, This tower can breach the upper troposphere and flatten at the top, forming an anvil shape. This is a cumulonimbus cloud, the classic thunderstorm engine. Inside that cloud, chaos reigns. Rising air carries droplets high into the cold upper atmosphere, where they freeze into ice crystals. These collide, combine, and fall. As heavier particles descend and lighter ones continue to rise, an electrical separation occurs. Positive charges gather near the top, negative near the bottom. The cloud becomes a battery, charged and waiting. When the difference in charge between the cloud and the ground, or between different parts of the cloud, grows too great, nature seeks balance. A sudden, violent discharge of electricity, lightning. Lightning heats the air around it to over 30,000 degrees Celsius, about 54,000 degrees Fahrenheit, in a fraction of a second, hotter than the surface of the sun. That rapid heating causes the air to expand explosively, creating a shockwave we hear as thunder. There's a reason thunder rolls. Sound travels more slowly than light, and as lightning snakes through the sky, it ignites air in a path, producing multiple overlapping shockwaves. What we hear isn't just one boom. It's a chorus of them, delayed and echoed through the atmosphere. Some storms remain simple and short-lived, called single-cell thunderstorms. They rise, rumble, and fade within an hour. Others, like supercells, are far more complex and dangerous. A supercell is a storm with a rotating updraft, called a mesocyclone. This rotation is often caused by wind shear, when winds at the surface and higher altitudes move in different directions or at different speeds. The result is a rolling motion in the atmosphere that can be tilted vertically by rising air. Inside a supercell, the storm becomes a self-sustaining monster with powerful updrafts, rotating winds, hail the size of baseballs, and lightning flashing dozens of times per minute. Some of these can spawn tornadoes, funnels of violently rotating air that touch the ground and carve narrow, destructive paths across the land. But even without tornadoes, storms can flood cities, fell trees, and knock out power. And yet, they can also be beautiful. Have you ever watched a storm roll in from the horizon? The way the sky bruises into shades of violet and green? The way the air thickens, as if holding its breath? There's something primal in that. A reminder that the world we live in is alive, and sometimes loud. Thunderstorms are also essential. They redistribute heat and moisture around the planet. They feed rivers and lakes. Lightning even helps fix nitrogen in the soil, making it available for plants. It's as if storms, for all their fury, are part of the Earth's renewal. Let's also speak of a quieter storm, the blizzard. Unlike thunderstorms, blizzards are storms of silence and drift. They begin with moisture and cold, bitter cold. Snow forms in clouds just like rain, through the condensation and freezing of water vapor. But instead of falling in drops, it crystallizes into delicate patterns, each flake a six-armed poem of ice. If the wind picks up and visibility drops below a quarter mile for more than 3 hours, we call it a blizzard. In these moments, the world becomes white and formless. Sound softens. Time slows. It's dangerous, yes, but also deeply, strangely serene. Then there are hurricanes, massive storm systems that form over warm ocean waters. These tropical cyclones gather heat and moisture from the sea and organize into spiraling systems that can stretch hundreds of miles wide. At the center, a paradox, the eye. Calm, clear skies. Light winds. Surrounded by the eye wall, the most violent part of the storm. Hurricanes are powered by the release of latent heat as warm, moist air rises and condenses. As long as they remain over warm water, they strengthen. But over land, cut off from their energy source, they weaken and fade. Yet in their wake, they reshape coastlines, floodplains, and sometimes entire lives. Why does the sky give us such powerful storms? Why the noise, the chaos? The truth is, storms are not expressions of anger. They are the atmosphere's way of redistributing energy, correcting imbalances created by the sun. They move heat from equator to pole, from ocean to land. They are the great balancers of Earth's system. And yet, they speak to something deeper in us. Something ancient. Maybe it's because our ancestors once huddled in caves while lightning split the sky. Maybe it's because thunder still rumbles in our bones, as if the earth is remembering something. Or maybe it's simply that storms remind us how alive the sky truly is. So next time you hear thunder roll, or see lightning lace the clouds, pause. Listen. You are hearing the voice of the sky. Not in words, but in energy, in light and sound and motion. And when the rain comes, let it fall gently on your roof like a lullaby. Let it remind you that even the loudest storms pass. And in their wake, the world begins again, washed and whispering. Now, let us rise gently from the fire of the storm to the edge of frost. In the next chapter, we'll explore how weather paints in white, through ice, snow, and the cold hush of winter. Chapter 6. Ice, Snow, and the Architecture of Cold. There's a stillness that only cold can bring. It hushes the landscape, dulls the echo of distant sounds, and slows the rhythm of time itself. Step outside on a snowy morning, and the world feels softer, as if someone has laid a blanket over reality. The air is crisp, your breath fogs, and the crunch of footsteps in snow becomes the only music. Cold is not simply the absence of heat. It is its own presence. A sculptor with delicate hands, it reshapes the world with precision and patience. But where does this chill come from? At its core, cold begins with the retreat of sunlight. When the sun's rays arrive at a shallower angle, as they do during winter months or at high latitudes, less energy is delivered to the surface. Days are shorter, nights are longer, and the Earth's surface loses heat faster than it gains. Once warmth fades, everything begins to change. Air cools, molecules slow, and water, the shapeshifter of weather, transforms. Liquid becomes solid, vapor becomes frost. Snowflakes form silently in the upper atmosphere, long before they fall into our waiting hands. Snowflakes are perhaps the most exquisite expression of winter's touch. Each begins as a microscopic particle, dust, pollen, or salt, suspended in a cold, moist cloud. Water vapor condenses onto it, forming a tiny droplet. In the freezing air, that droplet freezes into an ice crystal. As more vapor collects and freezes, the crystal grows, branching, stretching, forming intricate hexagonal shapes. No two snowflakes are identical, not because they can't be, but because their formation depends on so many tiny variables: temperature, humidity, collisions with other crystals. Each flake is a journal of its own journey through the sky. Why hexagons? It's due to the molecular structure of water. H2O molecules naturally arrange themselves in a six-sided pattern when they freeze. This geometry echoes outward as the flake grows, creating a perfect, repeating symmetry shaped by chance and chemistry. Some snowflakes form plates, flat, disc-like patterns. Others form needles, columns, or branching stars. Some are as small as a grain of sand, others, large enough to catch the light as they fall, spinning gently like leaves. And when billions of these land together, we get snow cover, blanketing forests, rooftops, fields. Snow doesn't just sit passively. It reflects sunlight with near-miraculous efficiency. This reflectivity is called albedo. A fresh, clean layer of snow can reflect up to 90% of incoming sunlight, helping to keep the ground and the planet cooler. In polar regions, snow becomes more than seasonal. It's an architect of landscapes. Over time, layers of snow compress into firn, a grainy intermediate between snow and ice, and eventually into glacial ice, dense and blue and ancient. These glaciers, born from centuries of snowfall, crawl slowly over the land, carving valleys and mountains. Their passage is slow-motion erosion, sculpting Earth's face like water once did but frozen in time. Ice doesn't only live on land. In the oceans near the poles, sea ice forms in flat, sprawling sheets. Unlike glaciers, this ice is formed from the freezing of seawater, its salt content lowering the freezing point slightly, creating briny, porous crystals. Sea ice grows outward from the coasts in winter and recedes in summer, breathing with the seasons. It plays a critical role in regulating Earth's climate, reflecting sunlight, insulating the ocean below, and influencing weather patterns thousands of miles away. And in the coldest corners of the sky, frost and ice paint the delicate details of winter weather. Frost forms when water vapor in the air skips the liquid stage and deposits directly onto cold surfaces as crystals. On a quiet morning, you might find a spider's web jeweled with lacework or blades of grass rimmed in white. It's nature's embroidery, slow, silent, and fleeting. There's also rime, formed when supercooled water droplets in fog freeze instantly on contact with surfaces like tree branches or fences. Rime often looks like white coral or feathers, soft yet stiff, and is common in mountaintop or Arctic conditions. Then there are ice storms, among the most dangerous types of winter weather. Unlike snow, an ice storm begins with a layer of warm air above a sub-freezing surface. Precipitation starts as rain high in the sky, but when it falls through the cold layer near the ground, it becomes supercooled, liquid below freezing temperature. Upon touching anything, trees, roads, power lines, it freezes instantly. What results is a coat of glaze, beautiful and treacherous. Trees droop under the weight, wires snap, roads turn to glass. There's an eerie silence during an ice storm. No patter of rain, no crunch of snow. Just a slow, steady accumulation of stillness. But not all cold is dramatic. Sometimes it's subtle, invisible. Cold air is denser than warm air. It sinks, pooling in valleys and lowlands. On a clear night, with no clouds to trap heat, this cold deepens. Such nights are still, quiet, and deeply peaceful. Ideal for the formation of radiation fog, which arises when Earth radiates heat into space faster than it receives it. In this kind of weather, your breath feels closer. Sound carries farther. Stars seem sharper. And within all this cold, whether it's a snowy morning or a glacial night, there's a quiet miracle. Life adapts. Bears hibernate. Trees slow their sap. Insects burrow deep. Snow itself becomes an insulator, trapping warmth beneath its surface and protecting seeds, roots, and animals from deeper freezes. What seems like death or dormancy is actually rest, conservation, preparation. Winter is not just cold, it is a pause, a recalibration, a reminder that stillness is a kind of motion too. And for us, it invites reflection. Wrapped in scarves and wool, we walk through snow-quiet neighborhoods. We drink warmth from mugs. We watch frost-etched patterns on windows like messages from some frozen language. The world is slower, yes, but also more present. Every footstep matters. Every breath fogs the air like a ghost of ourselves. In the end, cold weather, ice, snow, and all, is not the enemy of warmth, but its contrast. It makes the hearth more inviting. It makes the spring more anticipated. It reminds us that even the harshest seasons hold beauty, purpose, and quiet grace. And so, as we step out of the realm of snowflakes and ice storms, we prepare to lift our gaze again, up into the vast, looping pathways of global air. In our next chapter, we'll journey through the winds that connect continents, the ocean currents that whisper beneath them, and the great atmospheric engines that turn silently above our heads. Chapter 7: Global Winds, Ocean Currents, and the Planet's Hidden Engines. Step back from the weather just outside your window, beyond the breeze that rustles the trees or the cloud that shades your home. Now imagine the Earth, round and blue, cloaked in atmosphere, spinning softly in space. There, swirling across its surface, are rivers of air and ocean, flowing in great looping patterns. These are Earth's hidden engines, vast systems that move heat, moisture, and momentum from one part of the globe to another. They shape climates, feed storms, and gently determine whether your morning will bring frost or flowers. We begin with wind. As we've touched on before, wind is born from pressure differences. Air rushing from high to low pressure, trying to smooth out the imbalances caused by uneven solar heating. But when you zoom out, something curious happens. The wind doesn't move in straight lines. It curves, bends, and twists across the globe. Why? Enter the Coriolis effect. Because Earth rotates, anything moving long distances across its surface, like wind or water, appears to curve. In the northern hemisphere, winds are deflected to the right. In the southern hemisphere, to the left. This invisible nudge gives rise to Earth's great wind belts. Around the equator, we find the trade winds, steady breezes that blow from the northeast in the northern hemisphere and the southeast in the southern hemisphere. These winds were once the lifeblood of sailing ships, carrying explorers and merchants across oceans. Farther north and south, between about 30 and 60 degrees latitude, the westerlies blow from west to east. These winds dominate much of the weather in temperate regions, including the United States and much of Europe. Then near the poles, polar easterlies flow, driven by cold, sinking air. These three main belts, trade winds, westerlies, and polar easterlies, form part of a vast, dynamic system shaped by sunlight, Earth's rotation, and the planet's spherical shape. And riding high above them, like celestial snakes, are the jet streams. These narrow bands of powerful wind are formed at the boundaries of these larger wind belts, especially where warm and cold air masses meet. The most well-known, the polar jet stream, circles the mid-latitudes. When it shifts north or south, it can bring unseasonable warmth, or biting cold, to the regions below. Jet streams don't just blow in straight lines. They meander, forming large loops called Rossby waves. These loops can stall, allowing weather systems to linger, sometimes for days or weeks, bringing extended rain, drought, or heat. But wind is only half the story. Beneath the surface of the sea, another engine turns. Just as the atmosphere has its circulations, so too do the oceans. These ocean currents move vast quantities of water across the globe, distributing heat and nutrients like giant conveyor belts. Near the surface, currents are driven largely by wind. The trade winds push warm surface water westward across the tropics, while westerlies guide it back east at higher latitudes. These movements create swirling gyres, immense circular patterns of ocean flow. In the northern hemisphere, these gyres spin clockwise. In the southern hemisphere, counterclockwise. The largest of these is the North Pacific Gyre, home to the infamous Great Pacific Garbage Patch, but also part of the ocean's heat distribution system. But deeper down, the ocean moves differently. Here begins the thermohaline circulation, also known as the global conveyor belt. It's driven not by wind, but by differences in water temperature, thermo, and salinity, haline. In cold polar regions, surface water cools, becomes denser, and sinks. In some areas, like the North Atlantic near Greenland, salty surface water cools so much it plunges thousands of meters downward, pulling more water in behind it. This sinking water begins a slow journey around the globe, deep, cold, and nutrient-rich. It travels along the ocean floor, eventually rising again in other parts of the world through upwelling, where winds or coastlines push surface water away and deeper water rises to replace it. This conveyor belt takes about 1,000 years to complete a full loop, but its influence is massive. It keeps Europe temperate, brings nutrients to coastal fisheries, and helps regulate Earth's carbon cycle. Without it, the climate would shift dramatically, possibly into a deep freeze in some places or parched heat in others. And still these engines, air and sea, are not separate. They talk to each other, endlessly. When warm ocean waters influence the atmosphere, we get El Niño and La Niña, two powerful climate phenomena in the Pacific Ocean. During El Niño years, trade winds weaken and warm surface waters shift eastward. This change alters atmospheric circulation, bringing floods to South America, drought to Australia, and disrupted monsoons to Asia. The entire planet feels the ripple effects. La Niña is the opposite. Stronger trade winds push warm water westward, allowing cooler water to rise in the east. It can strengthen hurricanes in the Atlantic and shift global rainfall patterns once again. These cycles, collectively known as YNSO, El Niño, Southern Oscillation, are one of the strongest natural shapers of weather on Earth. And they remind us that even faraway oceans whisper to your local sky. Sometimes, these large-scale systems can grow unstable. Climate change, driven by the buildup of greenhouse gases, is adding energy to the system. Warmer oceans, melting ice, disrupted wind patterns, it's all changing the choreography. Some scientists worry that if enough freshwater from melting glaciers enters the North Atlantic, it could weaken or even halt the thermohaline circulation. That would send shockwaves through Earth's climate system, from Amazon rains to African monsoons to Arctic winters. But for now, these engines continue. They carry whispers across continents. A warm breeze in your backyard might trace its ancestry to the Sahara. A storm over your lake might have begun as moisture lifted from the Pacific. And if you listen closely, to the wind in the trees, to the hum of waves, you're hearing echoes of these global forces. The breath of the earth, inhaling and exhaling in long, patient rhythms. All of it connected. All of it in motion. So next time you feel the wind on your face, imagine the journey it took to find you. Across deserts, over oceans, down from the poles. Carried by Earth's hidden engines, spun gently by its rotation, and shaped by the sun's steady fire. Now, as our journey through winds and currents settles, we arrive at the doorstep of tomorrow. In our final chapter, we'll explore what the future holds, how weather is changing, how science is adapting, and how, in a world growing warmer and wilder, we might still find balance. Chapter 8. Climate Change and the Future of Weather. Weather has always been a story of change. Seasons turn. Storms come and go. Some winters are hard, some summers dry. But in our time, a deeper shift is unfolding. A change not just in the patterns of weather, but in the very fabric of climate. To understand the future of weather, we must begin with the difference between weather and climate. Weather is the moment-to-moment mood of the sky. The rain falling on your window today, the sun warming your back tomorrow. Climate is the average of those moods over long stretches of time, decades, centuries, even millennia. It's the personality of a place, while weather is its passing thought. But now climate is changing. And so weather, the way it behaves, the way it moves, the way it feels, is changing too. This shift is largely driven by something invisible: greenhouse gases. Carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O. These are naturally occurring molecules, but human activity has dramatically increased their concentrations. Burning fossil fuels like coal, oil, and natural gas releases vast amounts of CO2. Deforestation reduces nature's ability to absorb it. Agriculture and industry add methane and other gases. These molecules trap heat in the atmosphere, like a blanket wrapping around the planet. This is the greenhouse effect, and it's not inherently bad. Without it, Earth would be a frozen world. But too much of a good thing can become dangerous. Since the Industrial Revolution, global temperatures have risen by about 2 degrees Fahrenheit, 1.1 degrees Celsius. That may sound small, but this is the average for the entire Earth, including oceans and ice caps. Some regions have warmed far more. And as the atmosphere warms, weather patterns begin to stretch, twist, and fray. One of the clearest signs? Heat waves. Around the world, record-breaking heat is becoming more common. What used to be rare is now frequent. Cities bake under scorching suns. Nighttime temperatures stay high, offering little relief. These prolonged heat waves are not just uncomfortable. They're deadly, especially for the elderly, children, and those without access to cooling. But heat does more than make us sweat. It fuels other changes too. Warmer air holds more moisture. For every 1 degree Celsius increase in temperature, the atmosphere can hold about 7% more water vapor. That means when it rains, it can pour, harder and longer than before. Floods become more likely, especially in areas already prone to heavy rainfall. At the same time, warmer conditions can dry out soil, leading to droughts. These paradoxical partners, flood and drought, often arrive hand in hand, alternating unpredictably. Farmers watch once reliable seasons crumble. Crops wilt. Reservoirs shrink. Then there are storms. Hurricanes are growing stronger. Warmer oceans act like fuel, allowing storms to rapidly intensify. What might once have been a Category 1 storm can now explode into a Category 4 or 5 in a matter of hours. These storms carry more rain, stronger winds, and push higher storm surges onto vulnerable coastlines. Elsewhere, in the interior of continents, severe thunderstorms bring more lightning and larger hail. Tornado seasons grow longer, and the boundaries of Tornado Alley in the U.S. may be shifting eastward. And winter? It too is changing. Some regions experience warmer winters with less snow. Others see intense snowstorms fueled by extra moisture in the air. The polar vortex, once neatly trapped around the Arctic, can wobble and leak cold air southward, thanks in part to a warming Arctic and shrinking sea ice. The jet stream, that high-altitude ribbon of wind, may be slowing and becoming more erratic. As it stalls or dips, weather systems linger, leading to stuck patterns like weeks of rain or heat. What was once dynamic becomes stagnant, sometimes dangerously so. And all the while, the oceans rise. As glaciers and ice sheets melt, they pour fresh water into the sea. As water warms, it expands. Together, these forces are causing sea levels to rise, threatening coastlines and island nations. Cities from Miami to Jakarta must now consider sea walls, pumps, and managed retreat. Yet for all these challenges, the future of weather is not written in stone. It's being shaped, right now, by our choices. Scientists use climate models to explore possible futures. These models simulate Earth systems, testing what happens under different emissions scenarios. If we continue burning fossil fuels as we are, temperatures could rise another 3 to 5 degrees Celsius by 2100. But if we reduce emissions swiftly, shifting to clean energy, preserving forests, innovating in agriculture, that rise could be limited to 1.5 degrees Celsius or less. Even small differences matter. A 1.5 degrees Celsius world is very different from a 2 degrees Celsius world. The severity and frequency of extreme weather events grows with every fraction of a degree. So where does weather science go from here? In a word, adaptation. Meteorologists are improving forecasts using high-resolution satellite data and machine learning. Warnings are becoming more accurate and timely. Communities are learning to build resilience, planting trees in cities to cool streets, redesigning infrastructure to handle floods, creating early warning systems for storms and heat. Farmers are adjusting crop cycles. Engineers are rethinking drainage systems. Planners are mapping floodplains and future coastlines. Weather, once an afterthought in design, is now a central concern. There's also a deepening understanding that weather, climate, and justice are intertwined. The poorest communities, those who've contributed least to the problem, often suffer the most. Helping them adapt and ensuring they have a voice in shaping solutions is essential. And still, there is wonder. Even in the midst of a changing climate, the sky offers its gifts. A snowflake falling in perfect silence, a thunderhead glowing at sunset, the hush of rain on rooftops. Weather connects us, to each other, to the past, to the rhythms of the earth. Yes, it's changing. Yes, the road ahead is steep. But with knowledge, compassion, and creativity, we can weather what comes. We can learn to live with the sky, not just react to it, but respect it. And perhaps, in doing so, we'll rediscover something ancient. That we are not separate from nature's breath, but part of it. As we prepare to close our journey, there is still one final chapter to rest upon, where we'll gather everything we've learned and return gently to ourselves, carrying the science of the sky into sleep. And so, dear listener, we've wandered together through the invisible breath of the earth. We began with the wonder of weather itself, the way it shapes our days and dreams. We touched the warm curve of the sun's rays, felt the sky's shifting pressure, and floated gently among clouds. We braved the thunder, listened to the whisper of snow, and followed global winds across oceans and time. We explored not just how weather works, but how it moves us, through memory, through story, through the quiet power of nature's rhythm. You now carry within you the soft architecture of storms and sunlight, the language of ice, the breath of deserts, the spinning of jet streams, the future, uncertain but still ours to shape. So now, as your eyes grow heavy and your thoughts soften, I'll ask again, just as I did when we began. Where in the world are you listening from tonight? And what time is it where you are? And if you enjoyed drifting through the atmosphere with me, consider leaving a like or subscribing for more sleepy science. But for now, let's rest. Sleep well, fellow traveler. Good night.